Of course, it's a pleasure to be here. It's a great opportunity. Manchester is my academic home. I'm still part-time here, and very happy to contribute to this amazing place. So, things that I'm going to show today is a little bit about the concept, evolving concept of reliability. There is more and more involving aspects of flexibility and resilience that are relatively new in the overall context of reliability, primarily driven by weather and renewables. Now, let's just start with, I know that in a way our worry about delivering a future energy system is passing through integration, deeper and deeper integration of renewable energy sources, particularly wind and solar. However, obviously, this may be a little bit troublesome, and in order to do that, we need some help. And I put here, welcome back to the future. Why that welcome back to the future? Because effectively, what we're going to talk about today, at least in part, is the use of some technologies that are really now becoming established in the energy system we talk today and future. Based on these technologies. However, these technologies are pretty old, and in fact, they were the ones that allowed us to do great achievements, I would say. Do you know what this is? That's a fuel cell. Do you know which fuel cell? The one that landed on the moon. So the moon landing was powered by a fuel cell, so it was hydrogen, and we allowed us to do this. Do you know what this is? It's PV, and this is on the Hubble telescope. So you see that now we're starting talking as an energy system of technologies that actually are pretty old, and as I said, allow us to do already big achievements. Now we'll see what we'll be able to do with these technologies. But in the context of what I want to discuss today, I want to have a quick recap about classical system operation and the way that we deliver reliability in system operation. There's the classical power systems that historically has been driven in terms of temporal differentiation by need to supply demand in real time, ensuring security and real time balancing, for which we needed to forecast a little bit ahead of time, the day before, what loads would do typically, and then schedule generators a little bit ahead of time. And then months before, you will need to plan for maintenance of generators, fuel supply, and all that. And then, of course, years before, you will have to make sure that you got sufficient generation and transmission capacity so that in real time, actually, you can meet the demand. Now, in terms of market services, this is done in operational terms by making sure that sometime ahead you can dispatch or schedule the system in an economic way. This is done from typically day ahead to sort of real-time dispatch, which is close to 5 minutes resolution in most places now. And then in real time, you would guarantee system balancing, even if there is a problem in the system, you lose a generator, you use a line, by a number of ancillary services that really are there to maintain system stability at different times. So, for example, you have various frequency control ancillary services, but you also have a number of different services, including reactive power support, stability and voltage support, and all that. When you go to the planning stage, which is more months ahead, 2 years ahead, you talk about different sorts of contracts for example, maintenance planning or fuel delivery, to some form of planning that you would do in terms of investment in networks that, depending on the type of market, is done in a different way, can be fully centralized in some cases. So these operational aspects and planning aspects were well distinguished in the past, so much that you could, in modeling, assess years before if a system and network would be adequate or not to supply, for example, peak capacity when the peak demand were needed, without really worrying too much whether you would have in real time sufficient resources to be able to do that. Now, what's happening is that things are changing for a number of reasons. One is the fact that you have more and more power electronics interface devices connected to the system, and because of this you are losing so-called inertia, which is basically kinetic energy that is embedded in synchronous generators. Because most of renewables are not connected to synchronous generators, you are losing this kinetic energy that is effectively stabilizing the system in the very short term when there is a supply-demand imbalance. So this loss of inertia may potentially cause lots of issues, has already caused lots of issues. Additional to that, you start having lots of issues with ramping and flexibility, particularly because you have renewable energy resources that are partly unpredictable and very variable, so that there are much bigger requirements for conventional generators or other resources to be able to follow the ramps that are created by these new resources. On top of that, you need to be able to operate markets a faster time scale. Part of that is because technology allows to do so. On the other hand, the closer you get to markets, to real time in markets, the more you can actually enable some form of flexibility to be delivered, not only technically but also commercially, because you may have flexibility that is technically available, so capability of various resources to respond fast to given signals, but if this is not commercially profitable, then you will not do it. So the idea of having short-term markets that here simplified in terms of short-term economic dispatch is really to enable this flexibility to be delivered. Now, in the past, all of these were effectively very distinct processes. Now, you basically need to understand already in planning if you have enough inertia in the system, enough ramping capability, and everything else. So before in planning, you would only worry about having sufficient generation transmission capacity to meet peak demand. Now, effectively, you need to run operational studies, very detailed operational studies in planning to be able to do that. This is changing completely the kind of modern tools we have, but it's really motivated by the fact that the complexity is risen exponentially, not only in technical terms, but also in commercial terms. And in fact, when you look at the past and you look at who was providing flexibility, reliability, security in operational terms, well, they were primarily this kind of generation units, so the very fast units such as gas turbines, combined cycles to some extent, and some flexible CHP, if particularly they had a thermal storage. And of course, if you have a system that is interconnected, then you can also rely on various kind of interconnectors with different characteristics, depending on whether they are AC or DC systems. Now, things are changing very much because of the penetration of renewables, as I said, and here I put an example where you would, for example, see how, depending on the wind variation that you will have in the system, how the gas, the operation of the gas turbines would change significantly. So clearly, you see an anti-correlation between the availability of wind, so in this case very low, and the use of gas. So the variability of wind is changing significantly the patterns of operation of conventional generators. You would say, so what's the problem with that? These are flexible resources that are well used to ramp up and down. Well, it's not exactly so. Here I put a small example taken from work of a few years ago. There is no date there, but it's basically 10 years old. It's from when I was in college. They will look at how in a system with plenty of wind, I think this was like 30 gigawatts of wind with respect to a peak capacity, peak demand of the UK system of 55 gigawatts. So it would be about 50% of installed capacity of wind relative to peak demand of the UK system. I plotted here the utilization level of the conventional power plants, so the thermal generators. You will see that without wind, so in a system where there would be only conventional generators, there would be power plants from, say, this is the number of the various units. So this is a model, but sort of it was sort of developed by trying to reflect the reality of the UK system. So imagine that there are about 150 conventional generators, and then there will be some base load generators, about 50 base load generators with an average utilization level in the order of 85%, which is a typical utilization level of base load generators, also including maintenance and repair, for example, during summer. And then the utilization level of generators will go down up to less than 10% when you have the so-called peakers, so the very flexible power plants that would be used to follow the peaks. The moment they introduce more and more wind, as you can see, this curve here basically shifts it towards towards your left, so that effectively the utilization level of all generators would decrease to the point that you would pass from an average utilization level of about 50% to an average utilization level of less than 40% with wind. So all generators are on average be used less. Now, how, this is particular for the peakers, so this is zooming out the peakers part. And as you can see, there are generators. There are about 50 generators whose utilization level moves from below 40% to below 10%. So the peakers are heavily affected by the introduction of renewables. What does this mean in economic terms? It means that effectively, because you, as a conventional power plant, the cost of production of electricity will be a function of the utilization level, the capacity factor, the moment that you need also to recover the investment cost. You would like to produce more and more, well, as much electricity as you can, so that you can actually spread the investment cost over a large amount of hours of production. So obviously, if your availability goes down, so your capacity factor goes down, your specific cost of production, so the cost of every kilowatt hour that you produce, including recovery investment cost, goes up significantly. So when you look at this from an average point of view, say we said it's about 50% without wind. By the way, these slides also a couple of years old, so they are taken from my lectures actually in what was the name of the course? It's My Grid and Sustainable Electricity System. So they are coming from the course, but the principle still holds. So if you look at what average you have today, is about 50%, which would map around this average cost of electricity. When you look at the average fleet, then when you look at the average of wind and solar, where the utilization level will go a bit down, probably down to 35% or something like this, and the average cost would again go a little bit up. But as you can see, from here to here is not going up significantly. So on average, things do not look too bad. However, when you look at what the peakers do, because we said their utilization level is much lower because of the shape of the curve, effectively their average cost of production is substantially higher. So if you think now that peakers in the future would operate at a much lower level, you see that because of the shape of the cost curve, now their cost of production is significantly higher. So effectively what it means is that when you look at average utilization levels, things are economically not too bad. However, when you look at individual power plants, the ones that were they were already producing less, and they were the flexible ones. So the ones really needed also to guarantee reliability actually would be the one suffering the most. At the same time, their cost of production is going up, but at the same time, the ability to recover the cost goes down, because in the system you have more and more of these renewables that are pushing down on average the marginal cost of electricity. So, and on top of that, they also have fewer hours being dispatched to be able to recover the cost. So overall, it looks pretty bad for these generators. Now, these are, I said, slides literally taken from my classes here that we're teaching years ago. Now, is this science fiction or is this real? Well,
excuse me.
What? Please.
Yeah, for the previous slide.
I will never finish if you guys stop me with this. I'm happy to take. There are other 95 slides. So, okay, good. So you don't stop. So I'm very happy to respond later, of course. So now, what is the problem? Obviously, if you have this situation here, as said, if this becomes too expensive for these generators to actually be in the market, what comes next is that basically they go out to the market. It's pretty logical. But the interesting thing is that this really happens, because this is happening, for example, in Australia. When I moved to Australia in end of 2016, literally after 2 weeks, this was what was happening in South Australia, more and more renewables in the system, fewer commercial generators being able to provide reliability. Guess what happened? It was the famous South Australia blackout of September 2016. So everything was written, this is like textbook example. This is exactly what we were teaching in Manchester. So that's why the Australians should come here to attend our classes. Basically, maybe they would have avoided the blackouts. Everything was written in the textbooks, in our lectures that we were teaching for years. So there was nothing new. So when you say, is this science fiction so far future, it's already the past. This is the picture of when there was the separation event between South Australia and Victoria, so the system in Australia split into two, and one went down. This is how the frequency collapsed in about half a second, basically. Because when there was the separation event and then the blackout in one part of the system, effectively the frequency went down at a speed of 5 Hz per second. So obviously, 5 Hz per second means that in less than 1 second, your frequency goes from 50 to 45. You can't operate a system like this. There is no protection scheme able to respond that fast. So the system collapsed, and there were a number of reasons to do that, but primarily because of the policy, the Australian policy of pushing more and more renewables in a certain area of the grid, without thinking that that would cause reliability issues the moment that the providers of reliability will no longer be there, commercial generators in particular. So this actually generated like interesting work to do, of course, like when there is a blackout, it's always like this. So we were asked to perform the big piece of work for the review of the future secure generation electricity market. So the Minister of Energy asked the chief scientist to perform this review, asking a simple question: is it possible to have a system that is low carbon and reliable? Because if it's not, I think it's time to change the energy policy in Australia. Obviously, this is in an environment where there is lots of lobbying for coal and gas, because as you may know, Australia is very rich in fossil fuel resources. So we were asked by the chief scientist in turn to perform this kind of analysis, try to understand under which conditions you could operate a low carbon energy system, so with lots of renewables in a secure way. And the first thing that we looked at was not so much the sort of the technical aspects of the system, because these kind of things were pretty much known. There's just one equation that I'm not putting here, but I'm mentioning so as to make Joaquin and Will happy. So the equation is one. It's called the swing equation. It's the fundamental equation describing the dynamics of a power system that we study when we are in the primary school, pretty much. Not exactly. That's it. So we know the physics. It's not very challenging. So the chief scientist comes to us and says, okay, how come you guys, you're brilliant engineers, and then you can't make the system run? So the problem is not with the engineers. The problem is that with the economists who design the market without understanding the physics. So it's always like this. So there is no game. It's like Maxwell always beats Smith. Like physics always beats economics. There's no doubt about that. So if you do not understand how a market, how a physical system is changing, and that a market can no longer deliver on a different physical system, well, then there is no hope for renewables. So in the modeling that we did, effectively, we described how the market was effectively only looking at this part of the swing equation. So the market was designed to take care only of the steady state part of the response when you write a string equation, was not really dealing with the fact that in the meantime, in the real dynamic bit of the string equation, actually, we're changing the level of inertia, we're changing levels of kinetic energy. You could actually have a very fast rate of change of frequency, so the frequency could go down very fast, and have a minimum level of nadir that could be quite low if the physics was changing as it was changing in Australia at the time. It changed. So next, what we did was try to understand how you could map then the physics into market operation. So we developed this kind of security maps that would clearly show for different levels of inertia in the system. I won't tell too much detail. I mean, you can read the literature on this. How for different level of inertia in the system, you would actually have to change the way that you calculate your reserve services, and you will need to make sure that you are operating in a secure area. At the moment, all you are doing is you are calculating the reserves based on this line here. Whereas, obviously, if you are, for example, in a situation like this with low inertia, in this area the system is not secure because you will need to be in the gray area. So we did this piece of work. It was published as part of the sort of government reports. And then the system operator now is taken this work. It has literally implemented in Western Australia, which is a smaller system, subject to very high degrees of variability and pretty troublesome when you look at issue of inertia, where they have implemented this in their control room. So basically this model can be useful for them to observe in real time if the system is secure or not, so in case they can call for corrective actions. And now we're looking at more in detail how we could use this kind of modeling to inform also market design. In this market design, obviously, we need to understand that in the longer term, the system is changing anyway. So you have identified what was going wrong and how you can map the physics into market operation. But still, you're not saying which resources are actually participating in the market, and particularly that the new resources may be very different from the old resources. And in fact, we are transitioning from a system where flexibility and ancillary services in general were provided fundamentally by conventional generators, as we said. So everything was in the hands of transmission-connected conventional generators that were like few hundreds and very, very big. We're providing flexibility to an inflexible distribution system, where this system is changing to this direction, where now all activities are actually happening at the distribution level, because number of resources, smaller scale resources, including PV and batteries, are actually being connected to the distribution network, and then are being aggregated to potentially provide services to the transmission system. So there are more and more discussions about this, and this really is something that is required if you want the system to be able to operate in a stable way. So this is completely changing the philosophy, where instead of having conventional power plants, you talk more and more about virtual power plants, which effectively are the aggregation of distributed energy resources. They are controlled in a smart way at different aggregation level, from houses to districts to cities to what we call a smart grid, where all resources are intelligently interacting, and where system balance at the distribution level is actually messed up with system balance at the transmission level. So effectively, before the network was the distribution network was faster, that's why we talk about distribution network operator. Now the distribution network is becoming active, and you will need a distribution system operator to actually be able to perform local balance and at the same time to interact in an active way with the transmission system. Effectively, flexibility is now being provided by the distribution system, because in the transmission system, the conventional generators are basically disappearing to a large extent, and more flexible resources are available in the distribution system. And if you wish, the transmission system is now the one that is becoming inflexible or less flexible, because effectively large-scale wind, for example, due to its variability and other characteristics, is calling for more flexibility. So before, the transmission system was the one providing flexibility. Now it is actually the one calling for more flexibility. Now, who can help solving the problem? As I said, we understand now the physics, the environment is changing, and so on. Now, who is solving the problem? That's it. But this time, not going to the moon or other things. He's solving the problem by saying, after the blackout, going to South Australia and installing the largest battery in the world, 100 megawatts. Imagine how big this battery is, 100 megawatts. So, is this solving the problem, or is this the only solution to the problem? Well, in this sort of very simple scheme I put here, once you lose conventional generators, the next step is I will have a big battery here, and therefore the big battery could do something that is called fast frequency response, injecting very fast energy into the system, try to push back the response that was in a low inertia system to a response of a normal inertia system. So basically, by trying to replace energy available in conventional generators with very fast energy that will be available from batteries. It's not exactly the same, and there are lots of improper things that have been discussed about this fast frequency response, calling synthetic, digital, inertia, and all this. That's just a very fast response. It's nothing to do with what we call synchronous inertia. But in any case, the idea is once I couple a big battery, 100 megawatts at least, to renewables, maybe I can fix some of these issues, at least the short-term stability issues. Well, is this the best way of doing it? If you look at the big picture, you would soon realize that you want to decarbonize the whole energy system. This is the UK diagram, where it's 2014, hasn't changed too much. Effectively, you have most of inputs based on fossil fuels, and in outputs, you will have different energy vectors that are being used for different purposes, from transport to domestic to other uses and so on. When you look at this picture, you would realize that electricity is actually pretty small, because electrical energy is this pink color here, whereas you have this purple that is heat, and this sort of greenish color, whatever you want to call it, is transport. So it's all coming from fossil fuels, and the energy for electricity is actually pretty tiny. So if you try to decarbonize the whole energy system just based on just focus on electricity, you will miss out a huge chunk for gas, for transport, and all that. So part of this part of the solution is in going to electrification. However, we know that electrification would actually require huge investment in terms of capacity. So that's why you talk more about the integration of different energy systems. This concept of multi-energy systems, where you look effectively at how electricity, gas, and transport can be integrated in different ways. So when you integrate this in different ways, instead of having a battery, why don't you use the flexibility capability of houses, for example, through very flexible loads that is based on heat pumps, those kind of things, electric vehicles, of course batteries and PV, and in the future also hydrogen fuel cells, to try to do same job as batteries would do. And effectively, you can use, for example, building here as a virtual storage, where, for example, when needed, you switch off demand for air conditioning, and then you switch it back to reestablish the temperature level when it's needed. So effectively, this is a very interesting battery, because switching off a load is equivalent to discharging as a battery, and then having what is called the energy payback to recover the temperature is equivalent to charging your battery. So this kind of virtual battery is a little bit more constrained than normal battery, because of this physics has to happen in a pretty constrained way, while the battery can decide when to charge and discharge. However, it is effectively very similar to what a battery would do. Now, when you look at what you could do with a district energy system, for example, when you integrate again electricity and heat, you will see that in the future you could set up cases where you have combined heat and power plants, electric heat pumps, thermal energy storage, and boiler backup, where depending on the prices of electricity and the prices of gas, you can arbitrage between energy vectors, and then you can supply the consumers at least cost, but also doing the very right thing for the system. Imagine, for example, that electricity is very cheap because it's being produced by solar, wind, and all that. So what you would like to do is you would like to use as much electricity as possible. You don't want at the system level to curtail electricity, so you want to have more electricity usage. So what you would do is you would use as much as possible the heat pump to generate heat, and in case to store heat in thermal energy store. On the other hand, if you see that prices go up in the market, for example, because there is less wind, less solar, and the conventional power plants are bidding very high prices to recover their cost, what you would do is you would like now to start your CHP plant, playing with the spark spread arbitrage between gas and electricity, sell electricity to the grid, and again you would do this with a power plant that is relatively small. It's also producing heat, so at high efficiency because you are recovering part of the heat, and it's helping balance the system because the system needs now capacity because there is not much wind, not much solar. So this machine is actually pretty amazing because economically does the right thing, playing on this arbitrage between multiple energy vectors, and for the system perspective, it's helping balancing the system exactly as it is required. And when you do also the economic assessment of this, you will see that it's pretty good. How about transport? Well, there are different things you can do with transport. You know, this work that we're doing with Steve actually some time ago, looking, for example, how you could use electric vehicles, but not based on not based just on batteries, actually having fuel cells, so by basically using hydrogen-based electric vehicles to provide system support and ancillary services. So in other words, can you provide very fast response through electrolysers? They basically use electricity to produce hydrogen, and in turn is used then to supply these kind of vehicles. So can you use these electrolysers that are very flexible load instead of batteries? In some studies that we were doing, we, for example, identified in sort of test system how much of these services should be provided by batteries, how much should be provided by electrolysers. And then you would find out that once you have a portfolio of resources, very clearly the system would optimally allocate, and ideally the market should do the same, which resources should provide what. And these two technologies then become competitors, but they're also quite complementary. Because, for example, the electrolysers would naturally do a response that's got to do with frequency drop, because they are loads. So naturally, if there is a problem in the system, for example, you lose a generator, therefore the frequency goes down, you can solve the problem by switching off load. So if you have lots of load that is very flexible, then you can just do that. Same time, if you have a battery that can decide what to do by charging and discharging, it would be more natural for the battery to actually do more of a frequency response that has got to do with a frequency that goes up, the moment that the electrolyzer can do a response for when the frequency goes down. So there are some interesting schemes there that you start generating, and you look at a portfolio of technologies that actually can stay together in the future system, not necessarily competing. Now, when you look at the same sorts of application to Australia, you would realize that there is very little energy in general that is consumed compared to the amount of energy that is exported. So particularly coal and natural gas and uranium. So it's massive amount of energy that has been exported. In fact, the business case of Australia in terms of energy is not so much about generating locally. There's so much that is not ideal, but actually to export electricity. Now, what happens if in the future there is less demand for fossil fuels? Obviously, this can seriously damage the business case of the whole country. So the idea that the government is looking at very seriously is to say, well, we're well known for exporting fossil fuels. Why can't we try to keep business case about exporting energy, but instead of fossil fuels, we now export clean fuels, zero carbon fuels. How do you export zero carbon fuels? Again, by taking wind, solar, turning into hydrogen or ammonia, and then shipping hydrogen and ammonia to other countries. So effectively what you would do is you would ship out liquid fuels that have been generated from zero carbon electricity. So this is sort of new business model that the government is trying to build, and we're performing the studies, trying to understand how a clean electric system can interact with the hydrogen/gas system, so that on top of supplying locally your demand for electricity, heat, transport, and everything else by combination of electricity and hydrogen, you can also export hydrogen to supply other countries. When you do this, there are a number of interesting schemes that you could perform, looking, for example, at how you would integrate wind turbines, solar, electrolysers, hydrogen turbines, and all that. And it becomes really fascinating to see how you can really move from a system that before was purely electricity to a system that really becomes multi-commodity hub, where, for example, you still have areas of the system that are interacting with electricity and fuel. But at the same time, you are now able to export electricity, you are able to export fuels, like clean fuels, like hydrogen, and you provide also frequency control and ancillary services, fast frequency response, system start and ancillary services, and all that. So the moment that you integrate more and more these resources, you're actually able to change completely the business case of some regions of the system, and actually you are able to scale it up at a system level. At least we're trying to understand to what extent this can be technically done. I will skip this because it's a little bit technical, but effectively looks at, depending on the hydrogen cost and of that, what is the best way of performing the studies. Now, I was talking more and more about business cases, but effectively, how do you integrate in the market, in the system, very distributed resources with multi-energy characteristics with a centralized resource? So, for example, if you have a system like this connected to distribution level, where you have PV and batteries, diesel generators, demand response, and so on, how is this system interacting with the system market? Well, one idea is to use aggregation, once again. For example, when you look at the PQ curves of different generators, so for example, some demand response, some PV battery systems, some generators, you look at the PQ curves of different generators, and you can plot these PQ curves on this axis, this line. So when you aggregate them, what is the aggregation of this kind of system? Well, mathematically, this is a Minkowski summation, and as you can see, when you sum these areas, the sum is much larger than the sum of the areas. So this is a fundamental property of aggregation. When you aggregate, you get as an output that is much bigger than individual technologies. This is really the benefit of aggregation that you see in terms of flexibility of the PQ curve. However, and now for the electrical engineers, you will see that this starts looking like the PQ curve of a synchronous generator. So effectively, you aggregate resources, and these resources start looking like a real synchronous generator. Now, what do you do with this synchronous generator? Well, first of all, you need to realize that this synchronous generator is connected in a complex way to distribution network, and it is constrained by the operation of these devices within the network. So there are actually limits that are driven by what's happening in the distribution network. Then you will realize that effectively these generators can be actively controlled together with the grid, and depending on your capability of managing the voltages and the thermal constraints in this network, you can allow for different levels of bidding at this substation. It is the interface, my interface with the market. So effectively, this is really starting to look like conventional generators, because now, by manipulating the voltages and the currents in the system, and by allowing some active network management, in this case by using different levels of reactive power support, you can increase the level of power output that you have in this network. So when you do, what can you do then with the synchronous generators? Well, it's pretty obvious. You put it in the market. So now your distribution network is literally become like a generator, and this is sort of the concept of virtual power plant, and can play in the energy market. This is a reduced version of the Australian power system, by the way. However, is this enough? Well, it's not enough, because a real generator is also providing reliability services. And as we studied just earlier, what we really need in the future is the replacement of all generators that were provided by BT services with new form generation. So can we really replace a combined cycle gas turbine that was producing, it was bidding in the market, this kind of reserve services, with a virtual synchronous generator here? So is this generator able to do this? Effectively it is, and you can map the ability of the aggregation of resources to provide very fast frequency control ancillary services, reactive power services, and all that, and you can do it in a sort of environment and through modeling actually that is consistent with the way the current market operates, because you can also derive some form of cost functions for this. So you understand what your generator can do technically, and also how much it costs to move in certain regions. So effectively really developing bidding functions for as conventional generators would do. I will skip a couple of slides just to mention that these virtual power plants effectively can be developed to different scales, and now we are developing the feasibility study for a virtual power plant at the University of Melbourne. So this is the CBD of Melbourne, and that's where the new campus of engineering is going to be built. So there is $1 billion of investment in the new campus, and the idea is to build it as a virtual synchronous generator. So effectively, there is a feasibility study looking at 60 megawatts of power. However, different stages may reach 200 megawatts of power. So effectively, what we're discussing here is to have 200 megawatts of generation controllable load in the city centre of Melbourne, and then to develop that as a virtual power plant that can interact with the rest of the system. And we are performing the economic assessment for this. Now, and then I will conclude. We discussed everything when we, so far. Well, not really. What is this? How do you call this? Black swan. Do you know why it's called a black swan?
Very rare.
Very rare, yes. Why is it very rare?
They don't exist in the northern hemisphere.
That's it. So when the British explorers reached the Australian coast, they could not believe that there were black swans. So you don't know about something until it happens. And it is particularly bad, these black swans were very aggressive and dangerous when they would be very bad. So that's why we call extreme events, high impact, low probability events, black swan, because they are unexpected. You don't know they exist at times. So this is the issue of resilience. So very extreme events that can cause cascading failures, and these are the real events again that can cause a blackout. So this is like being really scared by the black swan. There are a number of events that are happening in Australia now. There is another separation event. In this case, 3 regions of South Australia separated: Queensland, South Australia, and the rest of the system, due to a mix of conditions. So the message is that because there are more renewables and because there are the system operation is more uncertain in general, we are no longer able actually to run the system properly. So we're really facing more and more resilience issues. So anytime that an event is a little bit stronger than before, we are really not able to deal with that. So there's lots of research going on. This is the dynamics of the frequency in the different states in Australia when the system basically split into three. So this kind of event is basically, the system operator can't do anything about this. They're not able to foresee it because there is a cascading dynamics that we're not able to model. So we're working more and more on that. And we're looking with different agencies into what is the best to do. Do we build a grid that is stronger and bigger, or do we make it smarter? So do we put more lines? Do we make the system more redundant, or do we make it smarter? Well, if you look at this, say you have this amazing battery. Are you using this amazing battery? Yes. This is what the battery did during the separation event. So this is the frequency, the blue one is the frequency in South Australia during the separation event. So the frequency is about 50 Hertz. Then there is a first event in the system, and the frequency goes down. At a certain point, there is a loss of an interconnector between South Australia and the rest of the system, and the frequency goes up, jumps up, and then it stabilizes. What was the battery doing in South Australia? Well, look at the green trace. This is the battery. So the battery is effectively following the frequency, mirroring the frequency. So there is a droop control of the battery that has got an activation delay of about 0.2 seconds, and then it is basically mirroring the frequency. So the frequency goes down, touches some thresholds, the battery responds, and the green is basically mirroring the blue. Then the frequency goes up, and the green goes down as a mirror. So this response is the most extraordinary response that you can see. I mean, this is the best dynamic response ever seen in the world. There's no conventional generator can do this. It's really impressive what this technology is doing technically. What's the problem? What's the catch? The catch is that is exactly this very fast response that caused the interconnector to trip. Because in a world where we used to, basically you would associate a very fast change in power flows to a very fast change in angles, right? We all studied power system, just say active power depends on the angles. So if the protection interconnector sees a very fast change in power flows, they will think that the angles are changing, therefore you have rotor angle instability. Because the protection don't know that now there is a DC injection that can be faster than anything ever seen. So the protection thought that the system was going rotor angle instability, when actually it wasn't the case. It was just this super fast battery that was helping the system recover from the previous event. So we are really not ready yet. And other things we're doing here, we're testing actually how, for example, the use of electrolysers could support system operation, so that actually you try to avoid this very fast operation of the batteries by using other technologies there. Now, just to conclude, really back to the future, with the famous statement by Edison, we make electricity so cheap that only the rich will burn candles. That's what he did in 1882. He opened the first power system in the world, first power station, and then he built first power system in the world so that it would be able to provide electricity to customers, and most important, to provide them with light bulbs that he wanted to sell. Because he had invented the light bulb, but he could not sell many because electricity did not exist. So first he had to invent electricity and then to be able to sell light bulbs. So Edison did this big magic, changing the world because he wanted to sell more light bulbs. What we're seeing today is a transformation that are getting close to the sort of stage, and we need to understand more and more how to integrate the physics and the economics, it won't really be successful. The more the government's just pushing stuff into the system without any understanding of the physics, so the more there is a disconnect between economists and engineers, I think the less likely is that we will see this happening in short term. However, I think we're moving to right direction. And these are just some concluding remarks and some acknowledgement. But I think the message is pretty clear, I hope. Thank you.